Hi guys, so today we're gonna knock out our fourth problem in this 5-part mini series. We are gonna continue to solve systems of equations in 3 variables. We are given the green light to solve by substitution or elimination, but if you know me, you know that we're gonna stick to elimination. So the first step is to make sure that all the equations are in standard form, so variables on one side, constant on the other. Cool. And then you're gonna pair up equations to make 2 pairs of equations to eliminate the same variable. So which variable should we eliminate? It doesn't really matter. Let me go ahead and number these equations. With your permission, we are gonna eliminate z, and I'm gonna tell you why I made the call. We have a positive z here and a positive z here. They're almost opposite. Well, they're not almost opposite, but it's very easy to make them opposite. We just multiply one of them by a negative and we're good. So that's the reason why I decided to eliminate z. But if you want to eliminate x or y, then go for it. So let's go ahead and make our 2 pairs. So I'm going to say pair 1 and 3. Why do I start off with those? Well, I start off with those because those were the equations that I used to help me make the call. But you can just pair up any 2 equations at random. It doesn't really matter. Okay, so hopefully I copied it right. So that's 1 pair. Let's go ahead and use another pair. We are already used equations 1 and 3, so for sure we're gonna have to use equation 2. Pair 2 with one of these 2 equations. I'm gonna pair it with 1 because the numbers seem to be a little bit smaller. So we're gonna pair 2 and 1, but I'll just put 1 and 2 just to make it easy on the eye. Okay, pair 1 and 2. So the equation 1 was 2x plus y plus z equals 1, and equation 2 was 3x plus 3y plus 2z equals 1. Okay, so let's go ahead and remind ourselves which variable are we trying to eliminate. We're trying to eliminate z. The coefficients are both positive 1 on z. We need a positive 1 and a negative 1. So with your permission, we're going to multiply the bottom equation by negative 1. So let's do this. Let's multiply the bottom equation by negative 1. The top equation was perfect, so that will give us 2x plus y plus z equals 1. The bottom equation, after we multiply by negative 1, should give us negative 7x plus 4y minus z equals negative 6. Please watch your signs. Most of the times when students don't get it right, it's not because they don't know what they're doing. It's just they're not careful with the arithmetic. So careful. Okay, so coefficients on the z are opposite because we're trying to eliminate z. So let's go ahead and add these equations. Okay, when we add the equations, that will leave us with negative 5x plus 5y equals negative 5. So 1 equation down, or 1 pair down, 1 more to go. For the second pair, to eliminate the z, we need a positive 2 and a negative 2. So let's go ahead and multiply the top equation by negative 2. Okay, and when we do that, will leave us with negative 4x minus 2y minus 2z equals negative 2. And that second equation, or that bottom equation, was perfect as is. So we take our time, verify that the coefficients are opposite. We don't want to run into a fun surprise. Let's go ahead, add the equations to eliminate the desired variable. So that will leave us with negative x plus y, these are out, equals negative 1. So it's like, oh, we got this. Okay, so again, how do we solve a system of linear equations in 3 variables by elimination? So step 1, make sure it's more like a prerequisite step. Make sure that all the equations are in standard form. Step 2, pair up equations and eliminate the same variable. Step 3, go ahead, join your equations to create a new system, solve that, and take it from there. Okay, so our new system is given by negative 5x plus 5y equals negative 5, and the second equation is negative x plus y equals negative 1. So now we're going to focus our energy on this freshly created system. So this new system in 2 variables has the x and y variables. So we want to find x and y before we can even think about finding z. Okay, so we're going to solve this by elimination because because I feel like it. Okay, cool. So in this case, which variable should we eliminate? It doesn't matter. The least common multiple for both x and y is 5. So we're just gonna eliminate x. Okay. So we want to eliminate x. The least common multiple between their coefficients is 5. So we want a positive 5 and a negative 5. We already have a negative 5. To get a positive 5, it's an easy fix. Let's multiply this bottom equation by negative 5. Okay. It's like, okay, we're on it. Find x and y and then find z. Okay. The top equation was already perfect. Let's go ahead, bring it down. The bottom equation, let's go ahead, distribute the negative 5, and that will leave you with 5x minus 5y equals 5. So gentle reminder, we're trying to eliminate the x. Coefficients are opposite, so we have the green light to add the equations to eliminate the desired variable. But this x didn't want to go out with the without a fight, because not only did the x's cancel, the y's cancel, and the constants cancel. So that will leave us with 0 equals 0. We were not trying to solve for 0. We were trying to solve for x and y so we can then find z. But in this case, so a reminder, if the variables cancel out for systems, whether you have 2 or 3 variables, you're going to stop and ask yourself, is this a true or false statement? And I'm like, oh man, does 0 equal 0? Yeah, 0 does equal 0. That kind of bums me out. Why? Because if the variables cancel out and we end up with a true statement, then that means that the system has an infinite number of solutions. Okay, you don't have to write this because this is not the answer. I'm not interested in how many solutions does it have. I'm interested in the actual solution set. Okay, so we're gonna have infinite number of solutions, so we should have these ordered triples. Okay, whenever we have an infinite number of solutions, we're gonna have to write our answer in set builder notation. Let's go ahead and introduce a parameter. So let me just go ahead, put that. Introduce a parameter. So a parameter is just pretty much a new variable that can take any value. So you can pick any variable of your liking. I like to pick u because we don't see it that often. Okay, so in this case, whatever variable you decide to pick, you know, I like to pick u. Some books pick r, some books pick s, some books pick v, but I like sticking with u. Okay, so in this case, we want to write x, y, and z in terms of this variable u. So the question is, how are we gonna do it? So this is my recommendation. Let me go ahead, come up. Okay, we're gonna go ahead, look at one of our equations from the system in 2 variables, you know, negative 5x plus 5y equals negative 5, and negative x plus y equals negative 1. Write down whichever one catches your eye. I'm gonna pick that bottom one. Okay, so we have what was that bottom one? Negative x plus y equals negative 1. And remember, we want to write all x, y, z in terms of this variable. So what are we gonna do? We're gonna solve this equation for one of those 2 variables. Solve for x or y. Which one is the best one? It doesn't matter. Okay, I'm gonna choose to solve for y because I don't want to deal with this negative coefficient. Okay, so in this case, if we choose to solve for y, let's go ahead, add x to both sides, and that will leave us with y equals x minus 1. At this point, that's when I'm gonna introduce formally the parameter. So I'm gonna say, let one of these variables equal u. Okay, should I let y equal u? Should I let x equals u? It doesn't matter, but this is my take. We want to rewrite all x, y, and z in terms of u. We already have a nice expression for y. Y equals x minus 1. So I would recommend you let this other variable represent u. Okay, so we're gonna let x equals u. Remember, what was our game plan? We want to write x, y, z in terms of u. What do we have? X equals u. It's like, oh, it's in terms of u. So 1 guy down, 2 more to go. Okay, so we have y equals x we're gonna substitute that, for u with u, because x equals u minus 1. We have x equals u. We have y equals u minus 1. Oh, we have y in terms of u. 2 down, 1 more to go. So now let's go ahead, write z in terms of u. Okay, so I'm gonna put find z. Okay. So we are gonna pick any equation and then solve for z. So I can't project all of my equations. The one that scares me least is the first one. So let me go ahead use the first one. Okay. So that first one, we have 2x plus y plus z equals 1. We wanted to find z, so we need to have expressions for x and y, and we do. Okay, so we have 2 times x. Let me go ahead, remind myself. We have that x equals u, and we have that y equals u minus 1. Okay, so 2 times x, which is u, plus y, which is u minus 1, plus z equals 1. Okay, so remember, the parameter is u, and we want to write x, y, z in terms of our parameter, which is called for like a new variable that can take any value. Okay, so let's go ahead solve for z. When we combine the like terms, the sum of the variable terms will give you 3u. Work your magic. I know you can do this faster than I can, but I need to take my time because this is how careless mistakes are made. Okay, work your magic, add 1 to both sides, and that will give us z equals negative 3u plus 2. So again, the parameter or the new variable that we introduced was u. We needed to write x, y, z in terms of u. We checked off x, y, and look at that, we wrote z in terms of u. Okay, so let's go ahead, write this in set builder notation. Okay, so we have an infinite number of solutions. So we have the set of ordered triples of this form. Where was I? X, which is u, y, which is u minus 1, z, which is negative 3u plus 2. Okay, but what's so special about u? Such that u is any real number. Such that u is any real number. Cool. And the question is, do we really have to write our answer like this? Do we really have to write it in set builder notation? Well, the answer is yes. Why? Because we have said that the system has an infinite number of solutions, and when that's the case, it's just not possible to list them all. Okay, so this is why we have to write it in set builder notation. Okay guys, that's our 4th problem. I owe you one more. Thanks.